The wedge void, or the wedge defect as some people call it, as you can see on the screen here, and you can see my pointer, and this is an extreme case, is typically seen as a separation or an opening or a fissure, as they call it, between the B-stage resin and the copper inner layer foil, typically on the B-stage side, which is typically here. As again, this is an extreme case. It's very significant, but it helps illustrate the possibilities of what can lead to this wedge defect or wedge void. When there is an opening here, what happens is that you can see how difficult it is to get electroplating and electroless copper back inside that wedge in that opening, and you often end up with a void or an area where the copper is so thin that it eventually fails in assembly or in the soldering operation. A lot of things can happen, and these are one of those defects that actually cut across a large swath of the printed circuit board fabrication cycle. Delamination, of course, is the separation of the B stage from the copper in some way, shape, or form. But what causes delamination? Well, typically, if the resin is not properly cured, you didn't use the proper lamination cycle for the heat up time and the cure time to ensure that the resin material is completely cross-linked, this can lead to the wedge or the opening. Certainly, over-aggressive chemistry in desmear, basically like alkaline permanganates, if they're too aggressive, or you choose the wrong solvent swell and it's not properly matched to your resin, you can get excessive penetration of the solvent into the resin, and then that ends up leading to an opening or a wedge. But don't discount drilling. Drilling is a very aggressive process itself. It generates a lot of heat, and it too can open up the wedge. So look at your drilling parameters, your feeds and speeds, your quality of your drill bits, and the other parameters related to the drilling operation. Here's a good example of the wall of shame, as you see on the left, and something that's done completely correctly on the right. You can see number one on the left, you see the situation where we have some nail heading, which is this flaring out of the copper inner layer. Again, typically, while it's not necessarily out of specification, you can see how that type of drilling, you can see the torn out glass bundles, and you can see an additional area here, how difficult, where the wedge has actually opened up just slightly, minimizing the plating thickness. Here on the right, where you see the 3-point connection from desmear, which was done quite nicely. Actually, we call this etch back. And I'm not necessarily advocating that you must have this good of a 3-point connection. But there are some applications and some specifications by end users that require 2 to 3 mils of resin, removed back into the whole wall, so you have that 3-point connection. What happens in cases when you don't have good control of your system, you end up with a wedge void because you're too aggressive on the desmear process. But in this case, it didn't happen. Why? Number one, the fabricator had excellent control of his drilling. Number two, the resin, the delamination cycles were in proper control. And in addition to that, the drilling was excellent. So was the process of desmear, where it did not overpenetrate or cause wedge voiding. This is another rendition of what we call the wedge void or the void crack. As again, you can see here just how and again, it's a schematic, just how the wedge can open up from poor drilling or improper cure of the resin. Again, going back to the lamination cycle in multi-layers. So we get plating, on the resin here and on the face of the interconnect, but because of that deep wedge void, it sometimes is very difficult to get copper back inside the wedge. And then, of course, you go through the rest of the process. You come out of electroless copper or direct metallization. You go into electroplating, and you find out that the electroplated copper does not plate all the way back into that wedge, giving you a thin copper deposit or none at all, or the copper is actually folded over on itself. So basically, when we have void crack, we get the failure of the electroless copper to not completely deposit into those recessed areas. And keep in mind, even though there's solution flow and solution movement, these types of crevices or deep gouges makes it extremely difficult for the copper to get back into these holes. So again, look at your drilling, your operation. And here's another example of an actual picture of the void crack. You can see on the whole wall here, you've got electroless copper, this light yellow line over here at the interface. You've got some 3-point connection, positive etch back, but look here on the C-stage side, here is your wedge. And you can see very little copper, if any, back into that wedge area. Again, all the suspects here, the usual suspects, must be looked at. Another situation that can happen where you may have in the boards that you can see on the right here, this may have passed electrical test at the fabricator, but because of the wedge void that you can see going around the hole here, it goes out to the circuit board assembly facility. They go through wave solder, and lo and behold, because of the thin plating like you see here, or the slight potential void or fold here, what's going to happen when that board hits the molten solder and it interacts with the flux? Chance for a blowhole or outgassing because of the copper wall is so thin here. And that's one of the big dangers of the wedge void or the wedge opening, is this potential for thin copper at that wedge that then becomes an area of weakness. So, and again, you don't have to dread the wedge void. There are several actionable items that can help you minimize or mitigate this issue. Obviously, the press cycle, the lamination cycle itself, heat up time, the pressure that you use to move the resin through the package, the stack up, anything you can do to minimize resin squeeze out and optimize the press cycle. Again, proper heat rise, proper use of the heat lagging materials. That minimizes resin squeeze out. That prevents what we call fat glass, or where the glass is actually pressed more on the copper instead of the resin, because that typically ends up causing that wedge to open during drilling. Drilling, as we said, is a pretty aggressive process, particularly for thicker panels. As the boards get thicker, minimizing the wedge void during drilling becomes a challenge. Some of the best drilling practices I've seen are using these newer drills that are what we call zindles. Their ability to rotate at speeds of 200,000 RPM. That helps to minimize the force of the pressure that the drill bit exerts when it's moving down, through the stack. So one thing you can do is drill one board high in the stack. Some people like to drill 2 or 3 boards for productivity reasons, but typically we know that typically leads to potential for wedge voids and or rough drilling. So adjust your drill stacks as needed. Chip load is another aspect area. Again, if your drill bit, if you have a high chip load, which is high rate of in feed or mils of feed per revolution of the drill, the rotational rate of the drill, one tends to get the drill bit more, instead of cutting, it's more like punching its way through the drill stack. And when it does that, it can easily cause wedge voids, not to mention rough holes, etc. Another area to minimize the drill, the post-drill situation with the wedge void is to bake the panels after drilling. This will help oxidize the resin, and then when you go through desmear, whether it's permanganate or plasma, you typically get a more uniform removal of the resin on both sides of the interconnect, both on the B stage side and the C stage side, which again helps us minimize the ability to cause that wedge to open. So again, uniform permanganate and or plasma will help minimize the wedge. Finally, we talked about bond strengths. How do we enhance the bond between the resin and the copper, and that goes into our, not just our multi-layer lamination press cycle, but also reads into and leads into the use of the surface treatment process, preparing that copper surface, whether it's an oxide alternative or conventional brown or black oxide, which allows the resin, when it flows during the lamination cycle, to coat that surface of the copper and hold those layers together. Anything you can do to enhance the bond strength between the copper and the resin system, between more uniform oxide coatings, better surface preparation, will also go into the equation of improving the ability of your oxide system or oxide alternative to make such a strong bond with your material that it will minimize that opportunity for the wedge foot or the opening. I hope you found that these actionable items will help you minimize the dreaded wedge void.